Okay, oops. So we have looked at limits this whole chapter. Let me write this down because I can't do two things at once. We've looked at limits this whole chapter. Now we're going to say, what is the concept behind it? Seems a little backwards, right? So kind of what we're doing today is called the epsilon delta definition of a limit. I want you to understand the basics associated with it. We will do the proof at the very end, but I want you to understand the basics of the epsilon delta, because that's how it's proven. So everything we've done so far is how you're actually going to use a limit. This is the proof and the definition behind why the concept of a limit works. All right, so we're getting mathy on you today. So limit of a function. Okie doke. We are going to, and I'm going to write the definition because it's good to know. We are going to assume f of x is defined for all x in some open interval containing a. That's an n. All right, except, just like everything else, possibly at a. Now, this is not new information, right? This is everything we've been talking about in terms of limits already. You get exceptionally close. You get right up next to it. That makes a limit. It's what it's approaching, except maybe not at the value. It can. That just means it's continuous, but it doesn't have to be a limit. So then we say the limit of f of x as x approaches a is L. Just exactly what we've been doing so far. As x approaches a, let me scoot it up a little bit, is L, and it is written in the format that we already know. The limit as x approaches a of f of x equals L. Okay? Now here's where we're getting into it. If for any number, and then it looks like a squiggly E, that's actually epsilon. It's the Greek letter epsilon, is greater than 0. There is a corresponding number delta greater than 0. There is a corresponding, let me squeeze this in. I've got my image here. I'll make that smaller. There is a corresponding number, oopsie daisy, delta, which looks like an 8, but you don't finish it off. It just stops there in the middle, which is also greater than 0, such that this holds true. The absolute value of f of x minus L, so I'm going to make these real thick so you know they're absolute value bars, is less than epsilon when 0 is less than the absolute value here of x minus a, which is less than delta. All right, that's the epsilon delta definition of a limit. So what we're saying here is that there is some value, epsilon greater than 0. There's a corresponding delta, which is greater than 0, just means positive, right? Such as f of x minus L is less than epsilon, where x minus a is less than delta. Now, here's the moral of this story. I'm going to make this a little bit bigger, and I'm going to make this, oopsie daisy, bigger so we can see it. All right? When I'm looking at this, f of x and L are the output values. Epsilon deals with those output values. That means that epsilon is this y correspondence, where delta goes with my x. All right? So what this says is I have some limit. So when we take the limit as x approaches a, all right, I'm approaching a here as x is approaching a, then my output is going to be my limit. So as I approach a here of my function, I am getting my limit, right? Okay, so the reason why we can do that, why we know that is to be the case, is because if you make this proof, then I'm saying, all right, so some delta value, all right, where x minus a, the difference between my actual x value that I'm looking at and my a value, has to be between 0 and delta. So from a, I'm going delta out from there. That's what it's saying. And it has to be a positive value. I'm either going to add delta to go to the right or subtract delta. So as I'm doing that, right, the distance around a corresponds with the distance around the limit. Meaning here, as I'm looking at going outside of the limit, there's some epsilon value. As I'm going outside of what I'm approaching, there's some delta value. Epsilon and delta, they're just variables. It's not that big of a deal. So that's what this is saying. My function minus the value of my limit, where I end up here, right? My x, as I'm approaching to the value that I'm taking the limit as approaches to, that's all that means. As I'm coming in from the left and as I'm coming in from the right, this epsilon value gets smaller and smaller, and I work my way in at the same time to get that actual value of my limit. All right? Don't get too wigged out about it. It's just using additional variables in order to bring that in. Okay? Okay. So let me give you an example, and I think that may help shore this up a little bit. So here's example 1. We are going to show that this graph here, that the limit as x approaches 3 of this function is equal to 5. All right? That's what we want to say. So from this, we can create our epsilon delta definition such that f of x minus 5 is less than epsilon whenever 0 is less than the absolute value of x minus 3, which is less than delta. So given the, oopsie daisy, given, oh, come here, you little stinker, this limit, so we know, right? We're looking at this right now. As x is approaching 3 as I'm coming from the left and the right, my limit is 5. We're just going to use this definition in order to prove it. Now, I'm not going to get all crazy on you, all right? Here's what I expect you to be able to do. Here's part A. I want to know what's going down when epsilon is equal to 1. I want to determine the value of delta. When epsilon is equal to 1. Remember, epsilon goes with those y values. So, if I'm looking at this, and 5 is my answer right here, and epsilon is 1, so this is epsilon equals 1. I'm going back here, epsilon is equal to 1. What I'm actually doing is I am following my graph over when epsilon is equal to 1. And then you focus where it crosses my function. And that's my corresponding delta. So if I'm coming down through here, this to get over here, delta is how much? If I'm coming down this way, to get over here, delta is how much? Yes. So when epsilon is equal to 1, delta is equal to 2. And literally that's all I expect you to be able to do with this. That's where your homework is coming out of here. All right, your goal, let me make it like this. Your goal is, once you figure out what your epsilon is, where is this hitting my graph? And wherever that hits my graph, then I bring this down and say, all right, from that A value, how far away am I going there? And it's 2, right? Okay, all the graphs that we're going to do are going to be symmetric, so I'm not too worried about that. But this is just basic knowledge. Again, I'm wanting you to hit the highlights, hit the basics here. What if I want to know what's happening when epsilon is equal to 1/2? All right, so this same graph up here, but from 5, epsilon is now equal to 1/2. So I have this value and this value, and then that's where I'm bringing it down. Do you see that? So when epsilon is equal to 1/2, my delta is equal to 1. Good, because it's 1 away. Where does it hit? You start with your epsilon. Oops, right there. You start with your epsilon, and then from your limit that you already know because you're given that value, then where does it hit my actual function? And then what's that corresponding delta? All right. That's the concept that I want you to be able to pull out of this. As I'm looking through here, what's that corresponding delta? Let's do one more. So here's a problem like what's in the homework, but let me make this a little bit bigger so you can see it better. All right. Here's what it's going to look like in your problems. So here we know that the limit as x approaches 3 is equal to 6. That's this graph. We already know that. That's what we have. We want to determine the largest value of delta satisfying each statement. So if x minus 3 equals delta, then f of x minus 6 equals 3. This is epsilon. All right. So if my epsilon is equal to 3, then I know from here, I'm coming over and it's hitting right here. Oh, come on, you little stinker. And 3 back, I'm coming over and it's hitting right here. And I have that going down. What is delta? Delta is equal to 2 because it's 1, 2 where this hits and 1, 2 on that side. So for this problem, delta is equal to 2. Do you see where that's coming from? If epsilon is equal to 1, you do the same kind of thing. I'm coming up here. I'm hitting it at 1, and then 1 away. I'm hitting it right here, and you do that same thing. What is delta? 1/2. That's an equal sign. Delta is equal to 1/2. All right. Where does my graph hit? When you determine where your graph hits, then you can get the delta that goes with it. All right. Basics is all I want you to get out of this epsilon delta. All right. This is what you're going to have for your homework.